In 1873, the philosopher Alexander Bain proposed his theory that interactions between neurons make up human thought. 85 years later, in 1958, a 30-year-old psychologist named Frank Rosenblatt created a machine he called the perceptron. In Rosenblatt's mind, the perceptron was a machine modeled to answer the questions of how information about the physical world is sensed. When connected to its eye, which was a camera with a resolution of 20 by 20 pixels, the perceptron was capable of very simple visual tasks like telling whether a point of light was to the left or right of it. Of course, that's not the impressive part, or the reason the perceptron was so revolutionary. The impressive part was that the machine was not programmed to do these tasks. Instead, it learned to do them, using electric motors to adjust its internal circuitry from an initial random state until it could perform the task it had been given. The perceptron was the first example of what computer scientists today call an artificial neural network, or just neural network for short. So what is a neural network really? Put simply, it's an interconnected web of simulated neurons. Like in the perceptron, neurons in other neural networks are adjusted automatically by a learning algorithm until they can perform a given task. These neurons don't work at all like the neurons in your brain, but they're organized in a similar enough way that, together, they can achieve some of the most basic capabilities of the brain. But that just sounds like magic, right? How does a neural network just adjust itself to perform a task? Well, you're right that it's not quite that simple. The neural network doesn't even know what its task is, for starters. Humans have to put in quite a lot of work, in fact, to tell the neural network what it's supposed to do. How do you tell a machine anything? Well, you might be thinking programming, but there's actually another way to tell a machine what to do. Machine learning researchers call it training. Training, in short, is when you show a neural network examples of what to do. This usually takes the form of an example input and an example of what you expect in return. When Frank Rosenblatt created the perceptron, he had to train it by showing it examples of what he wanted. For the perceptron, an example might be an input, like a light to its right, and the expected output, like a right signal. When shown this example, the perceptron would then change its internal circuitry, through some algorithmic magic, in a way that helps it give the expected output more often. With enough examples, a neural network can eventually achieve something machine learning researchers call generalization, where the neural network starts giving the correct output even when it hasn't been given an example of exactly what to do with a certain input. Because training only requires examples of inputs and the expected outputs, we can essentially treat a neural network as a black box. That is to say, we could ignore exactly what it's doing inside and just focus on what we're giving it and what it's spitting out in return. This arrangement between the neural network and the human is actually much easier to manage for complex tasks than standard programming. The black box effect means that you don't need to tell a network how to do a task at all. You just have to give it many examples to show what correctly performing the task looks like. This black box revolution has led to many of today's technological breakthroughs: automatic speech recognition, AI art generation, Google Translate, and most social media algorithms. In general, any computer-based task that you can gather training data for can be automated with neural networks. Wow, what a ride. So we can basically do anything we can imagine with neural networks now, right? Well, almost. I'm sure you've picked up on that training data requirement already. But one thing I've failed to mention up until now is that you need more training data the more complex your task is. Sometimes a lot more. DALL-E 2, OpenAI's image generator, was trained on hundreds of millions of caption and image pairs from stock image sites and the web to achieve the level of performance it has. Another limitation of neural networks is the cost of the training process. Itrex Group, a machine learning company, estimates that training even a very basic version of an image generator like DALL-E 2 would cost clients anywhere from $20,000 to $35,000 worth of computing power. So neural networks are, for now, not truly intelligent. They don't set their own goals or reason things out with logic in the same way humans do. As it stands, they're essentially superpowered statistical models recognizing the patterns between their inputs and outputs. But many machine learning researchers do have true intelligence in mind for neural networks. There may come a day when the pattern matching capabilities of current neural networks evolves into true human-level machine intelligence.